can hold their fucking horses. I'm sorry, here I am talking. I just, I have to get everything ready. I usually do all this when JJ's streaming. Everything's usually like I take my time in the morning and I get shit ready. And anyway, I wanted to show off. I set up a camera so that I can film myself taking it off the build plate, which is something that people like doing. They like they like seeing it. They like, hold on. People like this sound. People love this shit. Oh yeah. I got a bunch of glue on my fingers, dry glue. But that first breaking it off of the build plate, ooh, just yeah, that's the good shit. Oh, did you hear that? I'm gonna go back and play that. Yeah. Oh, it's like a back crack. You know what I'm saying? Anyway, yeah, I was just kind of like showing it off, being a badass. Because I'm a badass. Sorry. All right, hey, let's start the show. I finally got here, and I'm here, and I got I had Amanda helping me out. She was kind of like going like, "Let's go, let's go, let's go." No, she's all right. Where's let's start the let's do the intro. Let's do it. Oh, 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 oh. There we go. It's not echoey. Oh, it was echoey. Oh.
Wait, what?
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 Huh?
What? Oh. What? Oh.
Oh, the 28 years later new.
I'm just goofing.
Years
Goofing.
later,
New boot,
yeah,
goofing.
talking
Just
about
goofing. New boot, goofing. Genuine ostrich. 3 payments.
Story of armor.
Oh. 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 I'm just goofing. New boot, goofing. I'm just goofing. New boot, goofing. Genuine ostrich. 3 payments.
Oh. Oh. I'm here. I'm
I'm
early.
just goofing. New boot, goofing. Just goofing. New boot, goofing.
And,
Genuine ostrich. 3 payments.
I
Just
was
goofing,
led to believe that
goofing.
there was
New
going to be
boot,
a day
goofing.
wave.
Just goofing. New boot, goofing.
Essie lied to me.
Genuine ostrich.
Of
3
course,
payments.
there wasn't going to be. Of course, there wasn't going to be a day wave. I was an idiot. But anyway, I planned today like I was going to start an hour from now. Here I am, though.
Just goofing.
But we're
New
just
boot,
goofing.
Just goofing.
Right?
New boot, goofing.
You're just neighbor goofing.
Genuine ostrich. 3 payments. Oh.
There's another I Know What You Did Last Summer. We might have to watch that. I might have to pull that into the queue. Yeah, I'm probably going to have to do that. I'm probably going to have to pull that into the queue. Okay. Oh! Yeah. Where did I put the source? Like, you guys should know, right? Totally. Dead air. Awesome. Nice. Why isn't it showing? Oh, okay. Hey, we took a second. We're here. We're good. I'm going to work on Jeff here that I just printed out that you saw. Let me pull off the build plate. I'm going to work on Jeff, removing all the, the supports. And then after that, I just wanted to show off the size difference too, because I fucked up the sizing. Here. So this is going to shout out to Renee. She saw Miss Slaughter saw the Stitch glasses holder and asked that I should make this, and it wasn't gonna fit. Too small. I made it too small because I'm an idiot and I didn't check the sizing before I printed it out. Anyway, this should be better. Should be way better. Yeah, that's gonna be great. It looks funky, looks funny, just like Stitch. I know I gotta clean my glasses. I know. Where's my? I shouldn't use my shirt. But yeah, I can't read chat. I'm sorry. All right. So let's get into this. I got a cue, but it's not very long, and it was, again, I was really only planning on starting at 11, but it's okay. I'll do what I can. If you appreciate me going a little bit early, being a big boy, help me out here. Come on. I can do the whole like, share, and if you like, there is a let me move that out of the way. There are links. Yeah, let me put that over here, and then I'll put that, took it down right to there, and then I go down like to there. See? Push it over, make it even. There we go. Looking good. Then you can see the guys. You can see the guys. And you can see me work. Okay. Let's watch. Let's watch this 3D printer guy, do some wild shit that we do.
Building an enormous multi-stage EDF thruster.
Get over the voice. Get over the... Hey, stop. You in the back. Stop laughing. The guy made a fucking turboprop with a 3D printer, okay? Made a thruster with 3D... Stop. Stop laughing. I know his voice is funny. Stop it.
For many years, I've been fascinated by EDF thrusters, producing surprisingly high thrust for their size, and essentially being an electric version of the jet engine. Although EDFs are rather inefficient compared to propellers, their compact size and high output speed made them a good option for all sorts of thrust vehicles, as long as enough power can be provided. When researching the propulsion systems of electric aircraft, I found that one method to boost efficiency is using two sets of contra-rotating blades. This cancels out the thrust losses from swirling output air and more than doubles the thrust output compared to a single set of blades. Not only can this slightly reduce power requirements, but it can give an already compact thruster even more thrust for its same overall footprint. To test out this idea, I needed to find an ideal size and blade geometry that would be easily printable and get the best performance. The larger I can make the thruster, the better the overall efficiency will be, but being larger also adds extra cost, complexity, and weight. A good compromise seemed to be a rotor diameter of 300 millimeters, which is conveniently the largest diameter I can print as one piece on my CR10 3D printer.
I want a CR10
This will also
so
allow
bad.
for a thrust and efficiency comparison to the jet Scoter thrusters, which are also 300 millimeters. Moving on to blade geometry, I developed many blade profiles for various projects, but needed to find a way to compare them and approximate how their performance would scale. So I printed up 5 different designs with a diameter of 90 millimeters and gathered all the performance data to characterize each blade profile.
It's not super long,
Some designs are from past creations like Green Lightning or the Jet Scooter, and others were entirely new experimental profiles. So I tested each different profile on a thrust scale with a power meter and a tachometer so I could determine the blade constants and adjust variables such as pitch and blade count to best fit the motors I already had.
Okay, so he's doing as well as one can.
Using the data I gathered, I was able to...
He's actually doing some scientific data. Is it super duper accurate? No. Is it accurate enough? Is it accurate enough to get the data that he needs in order to get what he needs done? Yes. This guy's really fucking smart and
would scale,
he knows exactly
and how many
what
blades
he's
would
doing.
be needed for the motors I plan to use. Unfortunately, the most efficient blade design at small scale turned out to not be a good fit for my motors, requiring 24 blades to utilize all the motor's power. I found that this many blades would take significant blade losses and have a much worse overall efficiency. Surprisingly, the best performing design was Green Lightning's blade profile. Needing only 8 blades and being the second most efficient at small scale, this design was the best fit of all the tested profiles. I also estimated the full-scale thrust to be around 140 newtons, which is enough to be useful in a number of applications. I used 8 blades for the first stage and 9 for the second stage to cancel out the excessive blade-on-blade noise, which is a key drawback to contra-rotation. I started designing the full-scale thruster, and after several hours, I had a mostly finished model. I divided it into printable sections, which would be epoxied together later. Using a combination of PETG and carbon fiber nylon, it took a little over a week of non-stop printing and just over 3 rolls of filament.
Woo!
The only part that really requires a high-temp material like CF nylon is the motor mounts because the motors are tend to get warm.
We're still carrying that from a couple of hours ago. Nerds! Yeah.
It's often other printed materials.
Good callback. That was funny.
Once everything was printed, I glued together the components of the top and bottom cowling halves and filled any obvious gaps with filler putty.
Oh no, I don't
This was then sanded smooth.
No, I didn't. Thank you.
And given a couple
Thank you,
coats of
Renee.
paint for a smooth finish.
I didn't post
I
it.
used 2 electric longboard motors with a speed of
awesome.
170 kV and a rating of 70
I queued it up
each.
and then I didn't post
On a
it. See, I
14-cell
do all
battery, this amounts to a...
Again, I had to rush to kind of do this today. So thank you, Renee, helping me out for that one. That's good. Oh, did I fuck that one up? No, I didn't fuck that up. Okay. It's just not... It's not loading my, It's not loading my thumbnail. If people don't see the thumbnail, they don't want to click it. Let me try and fix that right now.
A total of 3,600 watts of maximum power per motor, or 7.2 kilowatts in total. When I started assembly, I made sure to run the motor and fan wires through the internal wire passages before the motors were bolted into place. Each motor is bolted on with 4 M4 by 16 mm machine screws, and each rotor is attached on top of the motor with 4 more of these screws. A 75 mm long, 8 mm diameter shaft with skateboard bearings can be inserted between the 2 rotors to stabilize the motors and ensure that the rotors rotate coaxially. Using thread-forming screws, I attached the front and rear motor mounts to the bottom shroud half. Installing a cooling fan in the tail cone ended up being very necessary because I would eventually be pushing my motors to the limit and exceeding the 7.2 kilowatt rating at full thrust. Finishing up the assembly...
Was that the legit... That was the video that he was taking.
...to the limit and exceeding the 7.2 kilowatt rating at full thrust. Finishing up the assembly, I used several thread-forming screws to securely attach the top half of the shroud. Using zip ties, I secured the cables and mounted the thruster securely to its thrust
Renee, man.
The thruster is now ready
awesome.
for its first test.
Yeah, the pay sucks, huh? Actually, pay me money. In fact, you give me money. fucked up. Oh, God. It doesn't want to... Oh, well. Thanks for telling me, Renee. I don't know why it doesn't want to do the thumbnail. Okay. Thanks. That was cool. Jesus. R.I.P. headphone users. Okay. This guy needs to figure out how to modulate his shit. Holy shit.
The maximum thrust came within
It's just
just
a thrust.
3
It's
newtons of
Mr. Footbag. It's
prediction
just
running
that
on a
he's just
14-cell
like
battery.
making a
With
3D printed thruster,
157.7
and it's
newtons, this outperforms the twin-engine jet scooter by about 6%. This is a small but significant improvement, especially considering that it takes up only half the intake area. Now examining efficiency. Can this thruster make enough thrust to offset its power draw? To calculate its power, I can use the single motor current and voltage readings and roughly multiply it by 2, assuming the difference in blades is cancelled out by the pitch reduction of the second stage. Ideally, I would use a larger current clamp, but this one already reaches its maximum, so there may be a few % error by measuring one at a time. With this method, I calculated the total power draw to be around 7.8 kilowatts, which is only slightly overrunning the motors. Comparing this to the 6.9 kilowatts of the jet scooter, it is apparent that the extra thrust of this engine comes at a cost in terms of power. Using watts per newton efficiency, the jet scooter thrusters come in at 53.1 watts per newton, and the contra-rotating thruster uses 56.9 watts per newton. This is 7.2% less efficient, but its advantages may still make it better suited for thrust vehicles and aircraft.
That's amazing.
Its high thrust density may reduce drag on the surrounding components, and it is much more convenient to strap on the back of anything with wheels and rocket on down the road. Considering the power levels involved, I recommend that anyone who attempts to build this to exercise extreme caution. I had to use most of my battery collection to power this beast of a thruster. Although I have run simulations and full-speed tests, the greatest hazard...
Those were all... These are all specifically made for, like, RC... they're lithium polymers, so they're... Wait, is that one? Yeah, that one's those are all lithium polymer. You really got to be careful with those. Be very, very, very careful with lithium polymer batteries. Discharge them if they're sitting. Don't leave them charged. Don't. You kind of have a tendency, if the wiring might be a little bit fucked up, they'll blow up. There's been people who've fucked up, plugging them in, and they overcharge it, they overjuice it or some shit, they trickle charge it or something stupid. And there was one guy, he got a piece of the battery, like, hit him in the chest, and it fucking killed him.
Of a thruster. Although I have run simulations and full-speed tests, the greatest hazard is one or both rotors exploding and sending flying debris. Never stand directly to the side while operating, and always wear safety goggles. Make sure all spinning parts are balanced to the best of your ability to avoid any excess vibration. For prospective builders, 3D model files are available for free through a link in the description. This has been a fun project to work on between all of my engineering classes and other failed thruster attempts.
Oh, he's an engineer.
I plan to continue optimizing this design for better efficiency, work on between all of my engineering classes and other failed thruster attempts. I plan to continue optimizing this design for better efficiency, motor loading, and thermal endurance. Hopefully this thruster design can prove useful and be a step closer toward electric aviation.
All right. Thank you, Aiden. That was awesome. Music time. No. Thought it was music time. Okay, 30 more seconds. What is he doing? I don't know what's going on. Oh, he was doing all of his batteries for how long it could go. Nylon eventually warped will be replaced with a metal mount. Cool. Yeah, look, you see the torque? You see the torque forces on those on the bolts? On the holes there? Yeah, those things are crack. Awesome.
My Baby Records. 12 contestants, one mansion,
Okay.
$1 million
I saw this.
with a twist.
Okay, so Wizards with Guns. These are the guys that did the, where they were from the future and they found a goon cave. and they thought he was someone of high status. Anyway, Wizards with Guns. I always feature their content here. Fucking love these guys. You have to subscribe to these people. They're finally getting some traction. It took them a little bit, but they don't really need my help. But here it is. Wizards with Guns. Yeah.
12 contestants, one mansion.
I bring this up because on Midnight Rift Party we've been going through a bunch of these these styles of shows, and this just hit that funny bone just right.
$1 million with a twist.
One of you will already have the money in their room right now.
What? One of us has $1 million?
I've never had $1 million before.
The game is simple. Vote out whoever you think is hiding the million and survive daily elimination.
If you're the last one standing, you keep the prize. This is Secret Millionaire.
Yeah. Morning.
Day 2.
I'm already a nervous person, and I don't even have the $1 million. So I just need to get it together and survive elimination.
Notice the subtle little these guys are they're so subtle, but they're also very overt at times. But the firefighter this is fake. Amanda, this is Wizards with Guns. They're like they make skits and they do like scripted content that is so fucking funny.
The $1 million. So I just need to get it together and survive elimination night.
I think Laura has the $1 million. She's been acting weird all morning. I hate to say it, but tonight, I might vote for her.
Hey, we should probably form an alliance against Laura.
Wait, you think it's Laura? I feel like Cassandra's been kind of quiet recently.
I don't know. I still think we need to keep an eye.
I don't know who it.
Just I know. I know. I know.
Banana phone. Pong ping pong ping pong ping. Banana phone. It's no baloney. It ain't a phony. My cellular, rectangular phone.
Because that's how we cut them up.
Banana phone. Ping pong It's no baloney. It ain't a phony. My cellular, granular phone.
Okay, shut up. There we go.
I don't know who ate all the money, but I'm not here to make friends.
What?
Guys, Devin barely touched his ravioli last night. Probably saving room for the $1 billion.
Oh my God.
We're not supposed to eat the money.
What?
Why did you eat the money?
Why did he eat it?
Did you think that was the game?
Oh my God, says literally the fattest person here. Josh, Teresa, you count hungry slut. You probably ate the whole thing in one bite. Dude! Chris, we should form an alliance. You and me have a real bond.
We need to take you to the hospital.
Shut the fuck up, Chris. You're literally chock full of cash.
Okay, let's have everyone return to our rooms. There's been a bit of a misunderstanding.
Don't worry, Tony.
Oh, fuck.
They can't even vote me out. I already ate the immunity idol. So, nice try.
Ambulance? Yeah.
There's no immunity idol.
Then why was there an immunity knob on the end of the door?
Oh my God.
Yes. He ate a doorknob.
He ate a doorknob?
And a bunch of money.
All we know for sure is the doorknob.
Am I fat?
I'm gonna go look for clues.
Hold on. I missed this the first time.
Am I fat?
I'm gonna go.
I missed that the first time. She couldn't get past that.
Look for clues.
Yes, familiar.
I think Josh could have the million. Because I heard him yelling a lot.
It could be inside any one of us.
I just don't know about what.
I just wanted to be friends with everybody.
I was trapped in my room all day. Some jackass ate my doorknob. I also think it's Trish. She's
jackass.
Really fat.
Next time on Secret Millionaire.
They bring that back up again.
Nice try.
Josh.
Yeah. That was hilarious.
I thought you said you wanted me to scream.
The outtakes are funny. That was fun. That was some racing. We're gonna do some music, and then we'll pop into. I forgot what I have queued up next. We'll figure it out.
My brother taught me how to chase the bag. Get right in the field, I had to make a bag. The day you lost your soul, wish I could take it back. I just wanna go get one more bag with my brother. Wanna be rich forever for my goals. Supposed to take you on your first trip on a private jet. A fight will always ball until I fall. We've been on this money game for years. Gotta drink this blood to make the pain go away. I've been driving these whiskey tears. Praying Keenaness don't go insane today. We went the high speed, forget the static. He wanted the rolling, I wanted the paddock. Gotta get the safe, my brother, mess around and drag it. I done seen a lot of things behind these glasses, yeah. My life going through many different phases. Gotta keep the thing on me, can't go to many places. Big 12 shows them in the drag races. And we were bag chasers before we had braces. I just lost my dog. Yeah, my brother taught me how to chase the bag. Get right in the field, I had to make a bag. The day he lost his soul, wish I could take it back. I just wanna go get one more bag with my brother. Wanna be rich forever for my dogs. Supposed to take you on your first trip on a private jet. A fight will always fall until I fall. Got the Burberry jacket and an ace of spades. Get 100 racks, I gotta make it today. Gotta get a tennis bracelet, punching you in the face. My dog looked out for me when I press on 30, then he put up in a jag or something. When the ops seen him pull up cold, yeah, they was mad as hell. Counting them hundreds back in Steely crib. I wanted to trip with my brother in Valentino for real. Remember I was talking to him on the jail phone on Christmas. Said when he get out, we gon' add the checkup like arithmetic. If you try to rob a brother, I thought I'd get the stick. I might slide on a brother like a ripstick. I don't know why all these legends gotta die young. Yeah, we gotta cut these snakes up out the grass. And everybody else suspected you last. Supposed to take these flights first class. I just lost my dog. Yeah, my brother taught me how to chase the bag. Get right in the field, I had to make it back. The day I lost my soul, wish I could take it back. I just wanna go get one more bag with my bro. Wanna be rich forever for my dog. Supposed to take you on your first trip on a private jet. I thought I always fall until I fall. I just lost my dog.
I think I did very
Hello.
good on this one.
You may have seen my previous video.
Oh, okay. This guy did what is probably one of the best 3D printed bearing designs ever made. For the 3D printing world, we kind of have like these like unattainable goals. One of them being 3D printing a working bearing, like kind of like a skateboard bearing or a wheel bearing for something small, obviously. I thought I had mine. I did that. I was successful. It was one of my early prints that I ever done. This is years ago. This is like 3 years ago. It's a 3D printed, fully 3D printed bearing. It's got a little bit of slop in it, but it was something that I did it. I was able to fine tune my 3D printer. It was kind of like an exercise for us 3D printer guys to, make a working bearing. Is it a good bearing? No. But this guy probably designed a pretty good one.
About 3D printed ball bearings.
Hey, John.
I use them with great success, but I found a better design. In fact, it's just the most popular ball bearing design in the world, slightly adapted for 3D printing. It beats my previous design in almost all aspects, and is probably the best design you can print. In this video, I will explain how to design and make deep groove ball bearing, and show you how to integrate it into your builds.
Well,
this type of bearing consists of only 3 parts: the inner race, the outer race, and the cage. As the name implies, there are deep grooves on both races. Let's draw them in CAD. That's actually very easy and will not take much time. Create a sketch and draw a line that will be our bearing axis. Draw a perpendicular line to the point that will be in between of races.
Yeah,
the length will define the size of our bearing.
I was kind of hoping you would.
Now draw an arc like this. The radius should... And then once again around this line. And we have our races. Balls through the gap.
Yeah,
so how are we going to assemble it?
There you go.
I've seen some people make a small hole like this, but we will use a different method. This problem was solved a long time ago by a guy named Robert Conrad. Here is his patent. His idea was to offset the inner race to create a large enough gap on the opposite side. That's why I made the gap exactly half of the ball's diameter. But to finish the bearing, we also need the cage. I designed it like this. Kinda a weird shape, but every feature here is for a purpose.
Yeah, you love... Well, I mean, you got to commend these people because he's obviously he's a Eastern European or Russian or whatever, and we're understanding him. I comprehend everything that he's saying. He's conveying high level stuff too. This isn't just, conversational English. He's talking about ball bearings and fucking engineering specs and shit. So, I'll give it to him.
Now I can print the bearing, and while it prints, I have a quick message about the sponsor of link in the description. Let's assemble the bearing. First, offset the inner race. Then fill the gap with the right number of rolling elements. Now we can carefully guide some of them to the opposite side, and the bearing is already kinda locked. Of course, balls can move freely for now, so we need to place a cage to prevent it from falling apart. To do that, we first need to evenly distribute balls, to have them somewhere around their intended positions. Now look at the cage shape. This feature will help us guide rolling elements to their place, and these slots will make the final click easier.
Alright, good for you, buddy. So you're using regular ball bearings, for some reason I thought for sure he was going to be using it was just going to be fully 3D printed. But, hey, man, this is pretty good, too. If all you got are a bunch of bearings and you need to figure out how to do a cage and you need to figure out how to make it work, this is great.
That's how you make the most common bearing in the world. The Conrad-style deep groove ball bearing. And I really like its simplicity. Even a simpler cage design like this would work. I just aimed for a slightly more convenient one, which is helpful if you are going to assemble them in tricky places.
Okay. This is great, dude.
If you are using on-shape...
I thought this was going to be a different video. Alright, so he's working on applied... on applying it to a flange. Good for you. All right, let's go to the next one. Sod wave.
Non-planar slicing has been a buzzword in the 3D printing community for
Oh, here we go. All right, guys. I'm super excited about this. This is the last video on my queue, and I'd usually be starting the show right about now. So, fuck it, we'll do it live. I'm super excited about this one. This was only a 7-minute video. This guy's fucking awesome. I think he has applied research papers to this, and I think this is how we're all going to do non-supports. These supports here that I'm spending all this time fucking clipping off and pulling off. This guy is gonna save the future of 3D printing. This is like real 3D printing now. This right here, this is 2.5 3D printing. This is not really like how you would think, because it's just sliced. It does one picture, and then it goes up another level, and then does the picture on top of that, and then does a picture. And so it's 3D printing, but it's just stacked 2D, okay? This right here, what this guy did, this shit right here, nickel, this shit right here, nickel, this shit right here, nickel, it's called cryptochronoconolite. This is the good shit. This right here is where we're heading. This is where I want this. I'm going to try and make this. I want this. This is what I want.
Non-planar slicing has been a buzzword in the 3D printing community for years, but now it's truly here.
Look at it. That's exactly how people thought it was going to look like. Notice how he's using a filament that will show... I wish I didn't give away the only printed version of this. I gave this the dragon that I made, where it had different colors going throughout the whole length of it. He's showing you like this is how it looks when you're doing non-planar 3D printing. It looks like this. I don't know how else to tell you that.
No more demos using manually written G-code, slicers that can only slice certain shapes, or 3.5 axis toolpaths. This is the S4 slicer, an open source, generic, non-planar slicer that can print any...
He said open source. I fucking love when it's on open source. Oh, yes! I'm going to make this. I'm going to make this. This is going to be made.
S4 slicer, an open source, generic, non-planar slicer that can print any object without supports. Many existing non-planar slicers rely on a human to plan the toolpath, whether that's by defining the surfaces to slice along, or by splitting the part into segments that can be printed with...
So this is the biggest fucking problem with non-planar 3D printing. This guy showed it. You have to define the planes yourself. If you're going to make a custom part and you're doing non-planar 3D printing, you have to make the fucking planes by hand. Fuck. That shit, and you gotta get real fucking. Look at all the yeah. So obviously, you know what this guy did here with this one was he defined a few of these planes, is what they're called, and then he let an artificial intelligence calculate in between his parameters. Anyway, this takes for fucking ever. This guy fixed all of this though.
Finding the surfaces to slice along, or by splitting the part into segments that can be printed with planar slicing. On the other hand, my non-planar slicer algorithm is entirely automated.
His algorithm,
given any arbitrary model,
so his algorithm that he uses to morph the part, it's funny looking. It's really funny looking to me. It's so you'll see it morphing the model, and it looks like it's fucking it up, but it's actually not. And it's very, very cool.
Planar slicing. On the other hand, my non-planar slicer algorithm is entirely automated. Given any arbitrary model, it is able to determine the best way to slice the non-planar layers to ensure printability and minimize support usage. Watching the simultaneous 4-axis toolpaths that this slicer generates is absolutely hypnotic. I'm still blown away with how the nozzle organically moves around the part to slowly build it up, taking paths that would be simply impossible for a human to generate by hand. A point that I really want to hammer home is that this slicer isn't just a demo. It can be used to print out functional parts or complex designs, the kinds of things I use my 3D printers for. In true RepRap fashion, let's print out a part from my Core R Theta printer. This is a B-axis mount, quite an awkward part to print on a traditional 3D printer.
Fucking A. I didn't really look at this part that he was trying to print out. Yeah, this is insanely complicated. The parts with the through holes, that's not that hard. But what's really difficult are those long, unsupported. I mean, obviously, you can see the supports there. But the long, unsupported tool path there. Wow. Anyway. Amanda, I would just print out dildos all day.
Normally I would print it in this orientation, but that puts the layer lines perpendicular to the torque forces on the part and requires support. On the other hand, the S4 slicer allows us to orient the part this way, which would be completely unthinkable with a normal slicer. But now, as you can see, the layers are in a better direction to handle the
I got the Canucks in chat talking about Canuckian stuff
on the part, and no support is needed. The S4 slicer is also quite well suited for miniatures, which are often designed with aesthetics, not printability, in mind. This squirtle looks cute, but it would be a pain to print with an FDM printer because of its huge unsupported overhangs.
I printed
the
one
S4
of those.
Slicer has no issues with it, however.
And yeah,
and the same is true for this baby T-Rex model.
Printing that one.
But the real magnum opus of
For
the
my
slicer
son.
is obviously the upside-down benchy, which I'm very proud of. It has some crazy toolpaths, and I'll get into how I managed to print this later in the video, which you really don't want to miss. A key limitation of my original printer was that the nozzle could only rotate 90 degrees outwards because of the end stop, something which would have prevented me from printing my upside-down benchy, which has 180-degree overhangs. So I reached out to JLC CNC, who helped me create these beautiful new extruder mounts, which have the end stops on the other side. They are CNC'd out of aluminium, making them ultra light and strong. They also provide an anodization service, which I use to make the parts red so it fits in with the rest of the printer. I've been using JLC PCB for years now and have always had a good experience with them.
Jesus Christ, they're sponsoring every fucking video I'm putting out there. They're actually really good guys. They'll make PCBs and they'll make fucking they'll machine whatever the fuck. Yeah, right there. Like you could do they can 3D print shit there for you too, and way better materials than I can ever fucking. Hey, no, don't get any ideas. No, they're not doing 3D printing.
The extruder mount and the aluminium PCB print bed.
They're not. Come to me. Get on my wait list and wait a month. I get a month-long wait list for 3D printing. All right.
CNC parts from JLC CNC is super simple. Just upload your CAD file, select
So
what
in order
material you want to build out of.
in order to complete this build, you're gonna need some custom. You're gonna need some custom shit. Is it gonna be? Look, is it gonna be like super cheap? No.
And it'll be made in just a few days. In my case,
Is
only
it
took 3 days to
reasonable?
make these extruder
Yes.
brackets, which is pretty incredible. So a big thanks to JLC CNC for sponsoring this
I mean,
video.
for what you get, it's super cheap. So
Also
yeah,
providing some really great
there's
cheap
your ad
services.
read. I'll
Now
let
back
you
to the
do
video.
it.
Given how complex these toolpaths are, you might be surprised by how simple the theory behind the slicer is. In fact, it all runs from a single Jupyter notebook, which you can run yourself. Let's quickly go through the algorithm because I think it's too interesting to skip. From a very high level, we're performing a few simple steps. Firstly, we deform our input mesh to remove all of the overhangs. We then slice the deformed mesh with a conventional slicer to get the G-code toolpath, and then finally we
So there's the magic right here, is the deform. He slices it. He deforms it so that it doesn't have horizontal overhangs. He deforms it. It lifts up everything and morphs it to the point where you could 3D print this. I could 3D print this thing right here.
We then slice the deformed mesh with a conventional slicer.
Just because there's no real like strong overhangs. I mean, other than the bottom part there, but that's the bottom part of the model. So you don't really have to think about that. But it makes it so that, you don't have to have supports for this kind of model, but it's deformed.
To get the G-code toolpath, and then finally we untransform the G-code back into the original shape, giving us our curved layers.
And that right there is the magic. That right, and you can see the toolpath, which is also why he chose that specific filament in the beginning. And I was trying to show it to you, like he was very smart in picking the filament that gradually changes from layer to layer. Anyway, that's the toolpath right there. And he didn't have to go through and define every single plane because all he had to do was make, we just went through it. Sorry.
This is exactly the same method I used for my simple radial slicer from my last video, except that the radial slicer
I'm like totally nerding out on this. This is the greatest.
This new generic non-planar slicer that I built.
It's generic and open source.
We triangle mesh into a tetrahedral mesh, which defines the object's volume. We then create a graph of the tetrahedral mesh consisting of the tetrahedrons and their neighbors. Each connection is labeled with the physical distance between the two tetrahedrons.
Okay, now he's getting really
heavy. This graph allows
heavy
us to run
into the
Dijkstra's
fucking...
to find the shortest path to the print bed for every tetrahedron in the mesh, which is pretty sick.
We'll
refer to this distance as...
This is some high level... Hey, Manda, you know how like the fucking Jesus. You know how earlier you were talking about how this is some high level fucking autism. This guy right here, holy shit.
Is a tetrahedron's path length property. We want to print from the base outwards, i.e. from lower to higher path length properties. Therefore, we calculate the gradient of this property by fitting a plane to the path length properties and finding which way slopes down. This gives the direction we should rotate every tetrahedron in to make the overhangs printable. We now want this rotation field to be smooth, so we use a nonlinear optimizer that tweaks the rotations of every tetrahedron to minimize.
He's walking through like every step that this program, this deformation program runs. He's walking you through every step, but it's like this happens, in the computer behind the scenes.
Minimize the difference in rotation between it and its neighbors. This is a super simple concept, but we're often working with tens of thousands of tetrahedrons, so the code needs to be really efficient. We then convert this rotation field into a continuous deformed mesh by framing it as another optimization problem. This time we're tweaking the locations of the individual vertices in the mesh to try and make every tetrahedron have the correct rotation, while also keeping the neighbors connected. This finally results in our deformed mesh, which we can slice and cure to get our G-code toolpath. Our final step is to untransform this toolpath from Cura into the shape of the original mesh. Every point in the toolpath lies within a tetrahedron in the deformed mesh, and we know how to untransform each one of these vertices, so we use a weighted combination of each of these transformations to move the toolpath point.
Okay, so he's throwing a lot of heavy at you real quick. But essentially what he's saying is that he's making this so that the computer's going to do all the heavy lifting. It's going to figure out how it needs to transform it and still be accurate from before transformation till before printing. He's making it so that He's walking you through. He's taking you by the hand, and he's spoon feeding you that this is, look, it's a research paper. This is how it's done, and it's going to be accurate. He's trying to, what he's doing right now is he's calming down us 3D printing nerds who have been sold this fallacy before, this non-planar, oh yeah, you could do this. He's trying to calm everybody down and be like, no, legit, this is open source. It's okay. It's highly accurate, because the few times someone has said like, oh, this is non-planar 3D printing, it's ended up being kind of like, oh, we still have to define the planes, or, oh, it's not highly accurate. Damn, that fucking sucks. Anyway.
Back into its place.
Yeah, he's making the computer his bitch.
We have some extra logic to prevent collisions during travel moves and extrusion compensation for the stretching and squishing that's going on. But after all of this, we get our final non-planar toolpath.
But look, I love how he's using that filament that changes from, you know, when you're doing planar 3D printing, it like gradually changes through the length of the part, but because of this new process, it's really fucking wacky, and you can really see the toolpath.
This whole algorithm is generic, meaning that it works for almost all of the meshes you can throw at it. The best way for me to demonstrate this was to slice the most challenging model I could think of, an upside-down benchy. This is especially...
Okay. Now I have to tell you why he's doing this, an upside-down benchy, and why he fucked with the model a little bit. I could just tell. This is another one of those like 3D printed bearing things where it's like, it's a challenge. And if you can do it, you're a god among 3D printing men and women. Sorry, ladies. But essentially this is like, if you could 3D print a bench. People calibrate their machines by 3D printing the benchy and then going, hey, look, see, it's really good. If you could do it upside down, throw it, flip it, and reverse it, you know, you're doing the fucking Missy Elliott on it. You're gonna, like, that's that you're gonna brag to people about that. Like, look at this, I fucking printed this motherfucker upside down. I made this my bitch, you know. So that's why he's doing it this way. He's doing it he's showing off. That's what he's doing. He's showing off.
Especially hard, as there are overhangs
he's
which are
gonna
greater
flip
than
it and
90
reverse
degrees,
it,
which means that they're essentially printing in thin air, requiring the nozzle to point upwards.
Look at that!
The algorithm identifies these sections by using the path to...
That's fucking bonkers to me! I know that seems like so weird to you guys, but I've been in this 3D printing world for a number of years. This is fucking bonkers. This is the wildest shit, and I love every second of it.
This is especially hard, as there are overhangs which are greater than 90 degrees, which means that they're essentially printing in thin air, requiring the nozzle to point upwards. The algorithm identifies these sections by using the path to base property again,
That's
checking if it goes
wild.
above the starting point. If it does, we know that the tetrahedron is printing in thin air and needs some extra rotation compensation. After a few iterations, we get this very splayed out benchy, which somehow doesn't have any overhangs. And when we slice and untransform it, we get this crazy looking toolpath where the walls are being printed downwards. I cheated a little bit by using a simplified benchy model to cut down on slicing times, which lacks many of the sharp features in the original model. But this model really stretches the limits of non-planar slicing, and I'm honestly really stunned that it was able to be printed at all. This is the culmination of months of work, and I'm really excited with how well it turned out.
So obviously, if you were to try and 3D print this, you wouldn't print this like upside down. And yeah, you could see how it's a little bit fucky-wucky on the corner there. It's a little stringy. But what he's doing here is he's showing, like, he's proving the concept. This concept is now proven, and you can replicate it, which is great.
The hot end takes these crazy paths around the benchy to slowly build it up, layer by layer, without any overhangs, and it's just really fun to watch.
One problem I do have is how is he cooling this? How's he cooling the model without getting in the way?
Hopefully this shows how generic the S4 slicer is.
It's
The
not-
fact that it's able to print this upside down benchy means that
I don't
most other
see a
models
fan. I don't see a part cooling fan. That needs to be figured out.
are a piece of cake in comparison. A lot of the fundamental concepts of this slicer came from the excellent work done by Zhang and Fang from Manchester
And as
University.
you can see, he has to use a special nozzle. It's like a spider nozzle, or what do they call it? Not spider. It's a Creality fucking nozzle. Mosquito. He's using like a mosquito type nozzle, which is not that efficient at retaining heat, which is probably why he's using it too. But he needs that long nozzle, giggity. And yeah, that's probably how he's getting away with no part cooling fan, is because it's starting to cool on its way out the nozzle, which is not good. You can definitely jam up a printer. I've had it happen to me. You have to you have to reheat the fucking thing. It ruins the part, by the way. Whatever you're printing is ruined. And it could ruin your hot end too. It could ruin your yeah.
A lot of the fundamental concepts of the slicer came from the excellent work done by Zhang and Fang from Manchester University, who published a paper on optimization-based non-planar slicers and released their open source code as the S3 slicer. I would highly recommend reading through their paper, or at least skimming through the excellent diagrams. My slicer builds upon their work using some new ideas, but I think the biggest feature of my slicer is just how simple it is. It all runs from a single Jupyter notebook, allowing you to edit the code and create visualizations to really understand how all of it works. Anyway, that's why I named my slicer the S4 slicer, the simple S3 slicer. I hope that this simple open source code base allows others to easily modify it and try out their own ideas, pushing this under-researched field of non-planar 3D printing forwards.
Somebody needs to come up with a GUI. Somebody needs to come up with a graphics user interface, put a nice, put a face to it, give it a nice, zhuzh it up. Put a cool ass dragon as the fucking logo or some shit. Whatever the fuck. It needs to have a graphics user interface. That's where all these fucking guys fall flat on their face. The reason Prusa Slicer is so prevalent is because it has a graphics user interface. If I have to use this off of a fucking Google Colab fucking virtual machine, I'm not going to use it. I don't like it. You lost me now. It just fell flat on its fucking face. All right, Ken Dog, really great. I love that everybody's cool at coding and you can all do Google Colab and good for you guys. But you're not gonna be as big as you want to be. You're not gonna. This isn't gonna get out to the people. This is just gonna be a niche fucking thing. If nobody puts it in a nice little fancy box and puts a nice little fancy bow on it for the masses, this isn't going to go anywhere. That's it.
It runs from a single Jupyter notebook, allowing you to edit the code and create visualizations to really understand how all of it works. Anyway, that's why I named my slicer the S4 slicer, the simple S3 slicer. I hope that this simple open source codebase allows others to easily modify it and try out their own ideas, pushing this under-researched field
Hopefully
of non-planar
somebody
3D printing forwards.
does it.
I hope you liked the video, and sorry that it took so long to get out. I spent countless nights toiling away at that Jupyter notebook, slicing parts and printing them out, only for them to destroy themselves after 2 hours.
Jesus Christ, that's a
But
lot
I'm really proud
that's
of the
a lot of fucking Hell yeah, that guy fucking put in the fucking work, though. I could tell you that. He may not have I may have took a shit on him there at the end with the fucking, oh, well, it's not easy to use. Meh. Look at that. He put in the fucking work.
Some bug in my code, but I'm really proud of the final product. I think that the combination of my very unique 3D printer, along with the crazy toolpaths generated by the S4 slicer, really...
He designed an open source and he gave it out for free. Can't fault him for that. Hopefully someone does come along and, you know, zhuzh it up.
Our sight to behold. I have tons of other projects planned for the future, so if you like what I do, feel free to subscribe. I have a lot of cool stuff in the pipeline, which you don't want to miss out on.
Did I subscribe? Yes, I did. Okay. All right. That's an hour for me. It's Tuesday, right? Yeah, it's Tuesday. Okay. If it was Wednesday, I was going to have to take off here soon, but I don't have to. Yay! So what do you want to talk about? Hold on. Let me pull up some music or something. I'll come up with something else to watch here in a minute.
Everybody plays a beautiful game while I'm in Brazil. Cause it's all you've ever wanted, and it's all that you want still. Don't you wanna play the beautiful game out in Brazil? I wanna play the beautiful game while I'm in Brazil. Cause everybody plays a beautiful game out in Brazil. And it's all you've ever wanted, and it's all that you want still. Don't you wanna play the beautiful game out in Brazil? I heard it lives down a river somewhere. The 6 cars and Chris in the bed. He got eyes, but he can't see. When he talks like an angel, but it looks like me. I heard it lives down a river somewhere. With the 6 cars and Chris in the bed. He got eyes, but he can't see. When he talks like an angel, but it looks like me.
And that was my triple collateral on free for all.
All right. Nope, we're going to hold that one for later. That one's going to be up next after these movie trailers. But you know what I have to do because we're doing movie trailers? I'm going to have to say goodbye to YouTube and Twitch. We're going to be Rumble and Locals only. I'm going to say goodbye, YouTube. Bye, Twitch. Bye.